Hi, I'm Keith Crandall, the Science Program Specialist at the Georgia Department of Education. Thank you for joining me today in this video, Three-Dimensional Science, Phenomenon Tasks and Assessments. The purpose of this video is for us to talk about three-dimensional science, for us to have some time to look at phenomenon tasks, to have some time to write phenomenon tasks, to look at some assessments, and also have time to explore assessment resources. When we think about three-dimensional science, it's helpful to look at this graphic. First, when we think about three-dimensional science in the classroom, the role of the student is elevated. Here, students' main tasks or their role is synthesizing information, investigating, communicating. With three-dimensional science, the role of the teacher is more of a facilitator or a coach to help students figure out a phenomenon, to immerse students in the science and engineering practices, to help students use the cross-cutting concepts as they explain or they develop an argument about a certain science idea. So today we'll explore this format as we think about phenomenon tasks. But first, a little bit of background. Our standards are constructed with three dimensions. The three dimensions are the disciplinary core ideas, or the content, the science engineering practices. I like to think of these as how students will be acting or creating like a scientist or an engineer. And finally, the third dimension, the cross-cutting concepts, the big ideas that span different science disciplines. And here we have students thinking like scientists or engineers. Another way to consider our standard construction is with this slide here. Here we have a 6th grade science standard. Every science standard in Georgia starts with the science practice of obtain, evaluate, and communicate information. We can see in the standard element, the first few words here, this is the science and engineering practice. In this case, the science practice is to ask questions. This is the how. This next piece, about where water is located on the earth, this is the disciplinary core idea, or the what. And finally, the why. Start with a phenomenon. This takes us back to that graphic where students are explaining, they're arguing about science ideas. And the phenomenon is the launching point. Let's dig a little deeper into that. Now, throughout this video, you'll see resources on the slides. These are all going to be linked in the document that's attached with this video. So a phenomenon is important, and here are some things that make a phenomenon effective. First off, an effective phenomenon has to require the core idea for a student to explain or figure out. In other words, as they work to solve or figure out that phenomenon, they're developing those core idea understandings. A phenomenon is observable. It's engaging. It drives the lesson. But at the same time, a phenomenon does not have to be phenomenal. In other words, we don't have to have these things that are way off the top and extravagant for it to be considered a phenomenon. There's also a distinction between a phenomenon versus a hook. We've seen that term when it comes to science instruction about a certain video or topic or demonstration being a hook, but really that's just to grab the student's attention initially. Whereas a phenomenon, it is present in the beginning of a lesson, but that phenomenon is going to be present throughout that entire instructional sequence. Some other things to consider with a phenomenon is this slide here about an ineffective versus effective use. For maybe a chemical reactions unit, there are a whole list of chemical reaction demonstrations a teacher could do, let's say in a physical science classroom. We can make things change colors, heat up, all kinds of engaging and fun things. But those kind of demonstrations don't usually have to be explained or figured out by students. But an effective phenomenon would be, maybe our students could look into water contamination, like how does lead make it into our water? And in the process of explaining that phenomenon, students are learning those core ideas. Another great resource for us to check out is the Georgia Science Teachers Phenomenon Bank. This is a free, searchable phenomenon bank. You can see on the screen here, you can search by grade, you can search by standard or element, and these are all submitted by teachers and science content specialists and leaders here in the state. An excellent resource. This is also linked in that document. But maybe a phenomenon isn't new in your classroom. Maybe you've been doing this for a few years now. So what's next? Here we're talking about the importance of the practice. The science and engineering practices represent students being scientists and engineers. This is how students are interacting with a phenomenon. The science practices require students to apply knowledge and skill at the same time. As students go course to course or grade through grade, they really build proficiency with the practices. In all of kindergarten through high school science, we use the same 8 science and engineering practices. One resource to dig a little deeper with the science practices is Appendix F. It's linked in the resource document. It gives grade band expectations for different science practices and is a wonderful resource to check out. But as we know, science isn't just a collection of facts. It's not a standalone collection of information. Students should be involved with the science practices in a much greater capacity than just that scientific method or that introduction unit. You see, the science practices with our standards really are a big difference here. They're social, they're creative, and it's an iterative process that students engage in. And the science engineering practices are meant to be immersive. And oftentimes, one science practice might connect very easily to another. And here, that third dimension, the cross-cutting concepts. We can use these in our instruction to provide students with real connections. And you can see the 7 cross-cutting concepts here. Things like patterns or cause and effect, the big ideas that span between earth science, physical science, and life science. These can actually be mental tools for students as they work through that phenomenon. Now, it might require us to do a little bit of direct instruction with these. So don't make the cross-cutting concept a secret. We might have to do something like, before teaching patterns in the periodic table, maybe we should talk about patterns in clothing, something that students can relate to before we start bringing that cross-cutting concept in with a science core idea. There's a resource to dig a little deeper into the cross-cutting concepts. It is Appendix G. It's linked in the resource document, and it provides grade level expectations that we can see with each of these cross-cutting concepts. So there's a little background about three-dimensional science. So moving on with this video, what is a phenomenon task? If we're going to spend some time writing these or looking at some examples, let's talk about what it is. Simply put, a phenomenon task is a student performance that is phenomenon-driven. It might have some formative and summative assessment components, but really it's a student-centered activity where they're going to be mastering that science and engineering practice, where they're going to be using cross-cutting concepts, and they'll be engaging with that core idea, all as they figure out or explain a phenomenon. And one important thing with a phenomenon task is we really need to be able to see student thinking. And maybe that's through them speaking or modeling, or writing, or so on. Let's take a look at some examples. Here we have 7th grade life science standards that deal with cell structures, cell organization, and body systems. And you can see here in the color coding, when students are developing a model or constructing an explanation, they're communicating that. And that kind of corresponds to the obtain, evaluate, and communicate there in the standard S7L2. So first, let's discuss what a traditional lesson sequence might look like for the 7th grade classroom we're looking into. Maybe we have some sort of opening or vocabulary exercise. And moving through, we have typical things like KWL charts or maybe some guided notes and modeling, and on to our assessment. And you can see similarly with the sequence with the body systems. I want to contrast this with a phenomenon-driven lesson. So here, the phenomenon we're talking about in this 7th grade example, it's about a marathon runner. I'll give you a minute to kind of skim through the slide here. So the question we're looking at, what could have made this runner so sick? This runner completed the marathon but doesn't remember parts of it and got very sick in the end. So this is the phenomenon. Students are working to explain what happened here as they go through this unit. So let's look at this phenomenon task. So here we see the phenomenon is introduced to the students at the forefront. And one of the first things that students do is they develop initial models about what's happening to the human body when we exercise. Now there might have to be some explanation about what a marathon is or the type of intense exercise that it might require to complete one. But as students move past the initial modeling, they start to obtain information about how that runner could have collapsed and what could have caused those problems. So they work through and they're looking to explain the causes of the runner's problems. Now you can see here in this slide, the things colored in blue, these are the science and engineering practices. In green, we have the cross-cutting concepts. So in each piece of a phenomenon task, or each part, students are involved with a science and engineering practice and a cross-cutting concept. It's an integral part to what they are doing and how they are working to explain that phenomenon. Now, eventually students will ask questions about the causes of the runner's problem, and they create a driving question board. So I want to look through some of these organizers and charts that you're seeing here for some examples. So first, students have this diagram, and they're trying to think or explain what happens during intense exercise. You can see a student example here on the slide. Things like the heart's going to be pumping more blood, the skin's going to be covered with salty sweat, but here at the bottom, you might feel like your feet are going to give out at any moment. But again, this is before science content. So students complete this at the very start of the structure. And that's a really key point with a phenomenon task. We have to get students thinking and working towards an explanation at the very forefront. So there was no front loading of content here. In other words, the teachers did not go through and cover body systems and cell structures before giving students these diagrams. And that's why it's so important that these are initial models. We can always come back to make revisions. And then as students read through this marathon story, they start to kind of build a timeline before, during, and after the race, what could have caused the runner's problems. And they also have a data sheet to consult. They compare this runner to other runners that were okay. And they also do this see, think, wonder chart, where they are trying to see data that's standing out at them, thinking about what might have caused the runner issues, but also in the wonder column, they're writing questions that maybe they need answers to. Now, all of these things for the marathon runner are linked in the resource document for you to check out. So you'll have the same exact graphic organizers and these models and charts too. Now remember, one of the cross-cutting concepts here was cause and effect. And even at the very start of this learning structure, students are building cause and effect because they're thinking about this before, during, and after timeline. Now, the effect they already know because they know the runner had issues or got sick or disoriented. But we're trying to work towards the cause. And part of that in this structure is building that timeline. Now, for some of these driving questions where kids, either in groups or on their own, are writing questions that would help them obtain information to explain what happened to this marathon runner, we get different types of questions. Some student questions might be about what kind of training did the athlete have? Or was the athlete hydrated or not? Maybe it's talking about their fitness regimen, or maybe their diet regimen that they were doing before this race, or their training possibly. So the importance of this questioning piece is that we're getting students to think about what happened to this marathon runner. Chances are students might have come up with the idea of hydration. Even if they're not athletes, they know what it means to be hydrated. And again, before any kind of front loading of content. So what students do next in the task, they kind of get at this hydration piece. And we can see here on the slide, again, for each piece of this phenomenon task, there's a science and engineering practice, and there's a cross-cutting concept linked with what the students do. So they have a little investigation here about how water movement has an effect on cells. And then students move to develop a model that would explain how these cell parts work together as a system. And you can see in step 3, the next piece, students are constructing explanations for how the cell membrane, the lysosome, and cytoplasm play a role in cell functions and could have caused the runner's problems. Let's take a look at some of these organizers that we used in this unit. So here we can see that students are using models as part of their explanation, in this case with a dehydrated cell or an overhydrated cell. And then on the right, they bring this back to the marathon runner. And part of the explanation piece is to explain how those cell parts work together to help carry out important processes. So hopefully you can see here how the phenomenon really does drive throughout the lesson. So students don't learn about organelles separate from the phenomenon. They learn about these organelles to help explain the phenomenon. And that's a key point with the phenomenon tasks, or phenomenon-based science teaching. The phenomenon's not just an intro, it's not just a hook at the start. It really is driving the lesson throughout. And beyond this, we could extend this to a biology level and maybe talk about macromolecules, where we could do organelles, but also we could talk about macromolecule structure and function. And here are some student examples. And you can see here, this is dealing with that third element in the standard about body systems. So even though at this point the students have talked about and learned about cells and cell organelles and organization, the phenomenon's still present here when they get to body systems. Because remember, at the start, students are asking questions about what could have caused this runner's problems. And chances are some of those deal with the body systems. So again, students are learning the core ideas as they work to explain the phenomenon. Hopefully that quick example made sense and it is helpful for you to see. There are more examples linked in the resource document for you to check out. In a little bit, you can pause the video for you to have a little time to write your own phenomenon task. Let's talk about some resources that can support you in this. The first are GSE planning cards. This resource is linked on the resource document. And here, there is a card for every science and engineering practice and a card for every cross-cutting concept. And what these can do is they give examples or student performance ideas for each and every science practice or cross-cutting concept. This can help us as we plan our instruction. So what happens next after this phenomenon task? Maybe this marathon runner can be an anchor phenomenon, a phenomenon that's present in maybe one large unit, or maybe a phenomenon that stretches more than one unit. We could get into how do human cells get energy. Now in the classroom we saw some pretty interesting results. Some of the teacher feedback we got with this phenomenon task was that students were consistently engaged. And they didn't see this like a normal unit. The student conversation was really neat to listen to. They were always working to explain that phenomenon. Now we get some questions about this of, well, what about time? If instruction looks like this, what if there's not enough time to get through all the material that we need to? But a few points here. Direct instruction also takes time. And we may not necessarily have to reinvent the wheel. We could bundle standards, meaning there might be one phenomenon that could connect more than one of your standards. But also, we can use the cross-cutting concepts in the science and engineering practices as learning structures, not just as secondary elements to the content. We could also assess these elements too. Another important thing to point out with this phenomenon task is the importance of using the language. And by that I mean using the language. We're talking about the language of the standards, like the science and engineering practices. So for example, maybe we could establish some classroom norms or protocols, like how can we build consensus on what a scientific model is? We may have to have some conversations or discussions with students about this, but it's important because as you can see in the example, students weren't just drawing cell models. They were developing models to explain the phenomenon. And we need to make sure we talk to students about that. Because again, that really elevates their role in the classroom. Now, some more student protocols. This might be challenging for students to have this elevated role. So maybe we have to talk about what each science practice is when we get there in the content, or possibly some examples of cross-cutting concepts when we need to use them. And I like to say this, it's kind of like the 5-paragraph essay. We could move from one class to another and know how to write a 5-paragraph essay. It might be on different topics or different levels, but we knew how to do it. And the same thing goes for the science practices and the cross-cutting concept. Students might go from one course or one grade to another, but the science practice and the cross-cutting concept stays the same. They'll know how to use them. So now on to writing your own phenomenon task. So here are some points on this slide. Number one, the importance of the practice. Maybe there are some graphic organizers that you can see. Those are linked in the resource document. Those might be helpful to get the science practice in the students' hands. We also mentioned the GSE planning cards and Appendix F. Check those out on the resource document too for ideas on what students can actually do with the practice. Now I'll say this. This can be really challenging at first. We can think of things for students to do, but let's make sure we give pause and think about, do those things involve the science practice? Do those things involve the cross-cutting concept? So, linked on that resource document is a collection of graphic organizers. These are editable. They are found on the wonderofscience.com. There's a graphic organizer for each science practice and for each cross-cutting concept. Oftentimes, these can be a great launching point for students. They're involved with a phenomenon. We put the science practice and cross-cutting concept in their hands, and this can really guide their thinking as they build understanding with those core ideas. So, now for the fun part. You can pause the video here and work on writing your own phenomenon task. On the resource document, you'll find resources to help you with this. One is a blank phenomenon task template, and you can download that and build it in the same way as you saw the marathon runner. You'll also see examples linked there as well. So, the general progression goes like this. As we discussed earlier, start with the phenomenon, and when we think about the student performance, maybe it's a group performance or individual or partner, whatever that may be, take the science practice with the cross-cutting concept paired up to do what that core idea expects. And we can take those directly from the obtain, the evaluate, and communicate. So consider color coding these like you see in the examples just to help highlight the importance of those pieces. So before you pause the video, think about how important that phenomenon can be. Check out those resources on the resource document sheet and think about materials or source that might be needed, but also think about how are students going to be engaging in the science practice. Think about what cross-cutting concepts would help students the most as they work to explain the phenomenon. So, go ahead and pause the video and have some time to build your own. Okay, welcome back. Here's part 2 of this video, dealing with assessment. So now that you had time to look at some examples of phenomenon tasks, and hopefully be on your way of writing your own, let's talk about assessment. So the science engineering practices and the cross-cutting concepts shouldn't be mysteries to the students. If they're going to be using these pieces as they figure out a phenomenon, our assessments should include these too. So I want to go over some resources and some ways that we can build these into our assessments. This first resource is linked on the resource document. It's a self-evaluation and reflection checklist for students. We built examples of these in every grade level or course in student-friendly language, and you can see in this example for 7th grade life science here that the science practice and the cross-cutting concept is still present. So students can reflect about their own learning as they develop those understandings of the core ideas. As they work to explain that phenomenon, they can use these to kind of guide their learning. And these are great checkpoints for teachers for us to maybe circle back with students or know what areas we may have to spend a little more time on. The next tool that's linked in the resource document is STEM Teaching Tool number 30, integrating science practices into assessment tasks. So the way this document is formatted is that for each science and engineering practice, task formats are given. All we have to do is plug in the specifics of a core idea or a phenomenon, and one of the great things is the task formats vary in complexity. Let's look at an example. So using this tool, you could see here on the screen, this is just a snip of that STEM teaching tool, and it gives us an example format or task format that we can use in our classroom. So here, the question or task students could do is, again, based on the phenomenon, but students are creating a cell model that shows interactions that keep a cell hydrated. Or we could present students with a claim about a phenomenon and ask students to identify evidence for that claim. In this example, we see a student claims that the marathon runner's problems were caused by interactions between cardiovascular and digestive. Students can then look through their evidence from class to support or contradict that claim. So consider using this tool to bring in those science practices. There are also examples of these linked on that sheet for you to check out. The next tool is STEM Teaching Tool number 41. Prompts for integrating cross-cutting concepts into assessment and instruction. Now, in a similar fashion as the previous tool, we have example formats given for each cross-cutting concept. They range in complexity. These could be multiple choice, or these could be left open-ended. Let's take a look at a couple examples. So in this case, if we're talking about systems and system models, we could be asking questions like, what can the parts of a cell system do together that individual parts cannot do alone? And again, in these example slides, you can see the importance of using the language that the students see in the lesson on the assessment too. They saw the science practice in the phenomenon task. They saw the cross-cutting concept in the phenomenon task. So these pieces should be a part of the assessment too. Another tool that's linked here is the assessment building template. Now, this kind of walks us through, after we've built a phenomenon task, to consider pieces like the science practices, cross-cutting concept, and it prompts us to think about assessment boundaries, maybe what kind of phenomenon or problem could be used. The template also prompts us to think about what barriers might be present for students in this assessment related to the science practice or cross-cutting concept. And then in questions 8 and 9 here, we can see that we're taking those things from the STEM teaching tools and building assessment items with them. And finally, there might be additional questions or varied formats of questions, maybe claim evidence reasoning and things like that, that we could pull in to assess students. So once again, you can pause the video here in a second, and thinking about the phenomenon task that you've started, think about writing assessment options that include the science practices in the cross-cutting concept. And you can think to include formative and summative. So the resources that we've talked about are all linked on the resource document sheet. So think about writing a collection of assessment items that align with the task that you wrote. Consider creating a variety. Maybe there's multiple choice or short answer, essay, or claim evidence reasoning, and bring those alongside using the 3 dimensions of our science standards. Thank you so much for joining me in this video. Please feel free to reach out to me through email or consider following us on our Twitter account. Thank you so much. Have a good day.